Well, we've done the mathematics papers, so let's move to the physics papers. This is level 2 physics. We're going to be starting with the 2025 exam, demonstrate the understanding of waves. And we're going to be using the formula sheet which is given to students, most notably these formulae here. And of course, I'm going to be trying to use the good old FX 98,000 calculators, which is the most common calculator used. For this one, I might actually use a few simulators as well. So without further ado, let's do it to it. So we're starting with geometric lenses. A data projector in a classroom uses a concave lens. So concave lens means that the focal point is going to be negative. It has an object which is 15 centimeters. So distance to the object from the mirror is the lens is 15 centimeters, and it looks like they're all in centimeters, so we don't need to worry about the unit. And the focal length is 10 centimeters, so it's going to be negative 10 by convention. A concave lens has a negative focal point because it's on the same side as the object. Draw and label the image in the diagram below. Well, it's going to be right there where they intercept. It's going to look like that. So it's going to be upright and it's going to be virtual. Not sure what else they want you to label, but that's about it. All right, calculate the magnification of the image. So for this, I think we need to find a few things before we do that. I want to avoid using these formulae here on the right. They're just a bit messy. Best to use this one on the left. So 1 over the focal point is 1 over the DO plus DI. We want to find M, but M isn't in here, but M is in here. And we need to find DI before we can do that. All right, let's do it to it then. So we're told that DO is 15 and the focal length is going to be minus 10 because it's concave lens. So 1 over F equals 1 over DO plus 1 over DI. It's a little bit like resistors in a circuit, a little bit like that. So 1 over negative 10 is going to be equal to 1 over 15 plus 1 over DI. We want to find what DI is. So 1 over DI is going to be equal to negative 1 over 10 minus 1 over 15. Grab the calculator, work it out. So minus 1 over 10 minus 1 over 15 equals minus 1 over 6. So that means that DI is minus 6, so it's 6 centimeters to the left. And then we know that M is going to equal DI over D0. In fact, that's going to be plus, isn't it? Yes, that's going to be plus. So DI over DO is going to be 6 over 10, which is 0.6. No, over 15. Whoops, my bad. Over 15. And that's going to be 0.4, isn't it? So 6 divided by 15 is 0.4, I think. Yeah, 0.4. So the magnification is going to be 0.4. And if we look at it, yeah, that kind of makes sense because the image which is formed here is smaller than that. It's to the left. So, yeah, this looks a little bit less than half. All right, fair enough. Now we're asked to fully describe the nature of the image formed. It's not a lot really you can say. It's going to be virtual because you can't project it. the thing you see is not the projection. It's going to be upright. It's going to be reduced, I guess you could say, and it's to the left of the lens. I don't really think there's much else you can put.
This question, I know, caused quite a bit of consternation in students, so let's go through it really, really carefully. And another projector, a convex lens, is shown here, is used, and a real image twice as big as the object is formed. Okay, complete a ray diagram grid below to show how the real image is twice as big as the object is formed. So it has to be a real image, right? Then they give you two other pieces of information. Make the object 6 squares tall. So in other words, HO is going to be 6, which tells us that HI is going to be 12. It doesn't tell us whether it's plus 12 or negative 12, but it is actually going to be inverted upside down. There's two possibilities. One I'm not going to cover, but there is one where we put the object here and the image here, and just so that and the image here, so the light sort of the lens kind of acts as a mirror, but we're not going to use that. All right, so that tells us quite a bit. We know that the magnification is going to be 2. And I've put there the absolute value of the magnification because we know that the real image, in order for it to be real, and we have the object on the left-hand side and the image on the right-hand side of the image, it has to be inverted. Okay, so let's use our clues that we've got. So if m equals 2, that tells us that the height of the object over the height of the image must be 2, which tells us that the distance to the image, around here, let's just change that. Height of the image must be twice as the distance to the object as well. All right. We also note from this that the focal point is 1, 2, 3, 4 units to the left and 4 units to the right with this convex lens. So that tells us that our focal point is 4. Our focal length, I should say, is 4. Right. Now let's do the maths here. So if the height is twice as much, that means that the distance must be twice as much, and the focal length is 1 over 4. So remember this 1 over f equals 1 over di plus 1 over do. We know that do is 2 di. So we need to do a little bit of maths now. I'm just going to move this down before we do it. So 1 over 4 is going to be equal to 1 over the distance of the image plus 1 over 2 times the distance of the image. I'm going to actually just move that because I'm getting twisted. So 1 over 4 is going to be equal to, and I'm going to double this one, I'm going to multiply by 2 over 2. 2 over 2 di plus 1 over 2 di. Now they have a common denominator, so 1 over 4 is equal to 3 over 2 di. We have one equation and one unknown, and we can solve this. So let's cross multiply. So 4 times 3 is 12. It's going to be equal to 1 times 2d is 2 di. So di must be equal to 6. That means the distance of the object must be equal to 12. This is twice as much. So that tells us a lot. It tells us that without even using the ray diagrams, that the object is be here, and it's going to be 6 pi, 1, 2, 3, 4, 5, 6, and the distance to the object must be on the other side, so it's going to be 12 across. So here's 4, 5, 6, 7, 8, 9, 10, 11, 12, and that's going to be 12 down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So our object is there. Our real image is there. Magnification is 2. And now if we use straight lines, it's here. First one is the parallax ray, and we're going to put that through focal point there, and it's going to go down to there. And then we have from top through the origin point, and it's going to right there. And you can just leave that one there. So this is going to be the object. This is going to be the image. And that's how you would do that. I'm going to show you I'm going to test it using a simulator. So the simulator is on OPhysics. I'm going to leave the link in the description. We have a little bit of a problem here because it doesn't actually go to 12 up and down. So what I've done, I'm going to divide everything by 2. So the focal length here is, this one is at -2, this one is at +2. It's already in that nice Cartesian form. It's a good way to remember it. If it's to the left of the lens, it's just like a graph. It's -2 and then +2 on the right hand. Positive up, negative down. So for this, we're going to get the object and we're going to halve everything. So this is at negative. The focal point is at -2. We worked out that the object has to be 6 out, which is going to be 3 in this case. So I'm going to move this as much as I can because it doesn't quite snap. Can I get it pretty close? I'm trying to move it ever so slightly. It's not going to do it. Is it pretty close? So the height of that object has to be 3. Oh, and it snapped to that point. Okay. So here the length is 3, so double it is 6. Here the focal point is -2, so double it to -4, +2, and sure enough, the image that we get is inverted. It's at -6, which means it's -12. So complete the ray diagram below to find and draw the image. Well, the ray diagram, we're always going to use the fact we could actually use the center of the circle, but it's not actually taught at this level. So the first ray is going to be like that, from the focal point to the top of the object, and that's going to go parallel there. So that's going to be the height of our object. It's behind the mirror. It's not really there, so it's going to be a virtual image. It's going to be upright, not inverted, and it's going to be enlarged. Next thing we have to do is we have to have the parallel ray here, and again it's where it hits the axis, not where it hits the mirror, and then our focal point is going to go up to that point there, and it's going to continue through until it hits this ray, and this is going to be our image. So you only really need those 3 rays. You could kind of make it a bit fancy by doing the center of the circle, but you're going to get the same result anyway. And also you'll probably want to draw a straight line, to save itself. Question 2. So a double glazed window has 2 panes with a refractive index of 1.5, separated by a gap. Matthew notices that a red laser shone through the window does not travel straight through. He's a pretty smart guy. On the diagram below, show the path of light that it crosses from one glass pane to the air. Put the mouthful there. So this is going to be theta 1, and this is going to be N1. You don't need to put this, but I'm going to put it in. And this is going to be N2. N is the refractive index. So this is the angle of incidence with the normal, not with the barrier itself, boundary itself. And it's going to bend that way. So theta 2 is going to be greater than theta 1. You have to be really, really careful here because, of course, glass to air, it's a heavier to a lighter medium. So a phenomenon called total internal reflection becomes an issue we're going to probably get to, 100% chance we're going to get to later, in which this boundary acts less as a boundary and more like a mirror. So just keep that in mind. N1 is 1.5. The refractive index of air is going to be pretty close to the refractive index of a vacuum, which is 1, right? The refractive index of air, I think it's 1.001, something really, really small, but pretty close. And that means that the speed of the vacuum will apply. So I'm going to say that the speed of light in a vacuum is going to be pretty damn close to the speed of light in air. Right. Explain what a refractive index of 1.5 means in terms of the speed of light in the glass. So the 1.5, if n is 1.5, and n of vacuum, which is the speed of light, which is given here, is 3.00 times 10 to the 8 meters per second. What does that mean? Let's apply this formula here. So n1 is 1.5. N2, the speed of light in a vacuum, is 1.0. So 1.1 is that. And the velocity through the second medium is given here as 3.00 times 10 to the 8. Let's work out the velocity 1. So N1 over N2 equals velocity 2 over velocity 1. So 1.5 over 1.0, which is 1.5, is going to be equal to velocity 2, which is 3.00 times 10 to the 8 over velocity 1. How are we going to do the algebra? We can multiply both sides by VI and then divide by 1.5. So V1, which is the speed of air in glass, it is going to be times 10 to the 8 divided by 1.5, and that's going to be times 10 to the 8. 3 divided by 1.5 is 2. So that tells us that the speed of light through glass is 2/3 of speed of light, which is c, which is the famous c equals mc squared. That is c, which is the speed of light through a vacuum. So when light hits the glass and goes through the glass, it slows down, and then incredibly it sort of speeds up depending on the medium that it's going through. There's a little bit more advanced than level 2 physics going on. So now we're told that a red laser with a wavelength of 6.5 times 10 to the -7 meters enters a different window with an incident angle of 30 degrees. So theta 1 is 30 degrees. And the wavelength of the red light as it passes in the glass is 4.64 times 10 to the -7. So this is going to be lambda 1. This is going to be lambda 2. And we're told to calculate the angle of refraction as the red laser passes through from the air into the glass. So in other words, N1 is going to be 1.0. And here they kind of give you the information that you were looking for in the last question. But you could always go back. All right. So we've got theta 1, we've got theta 1 is 30 degrees, lambda 1 and lambda 2, and we've got n in order to work it out because we're going to use Snell's law. So we're going to use this little formula here, and we don't need the velocity. So n1 over n2, and n2 is what we're trying to work out, is going to be equal to theta 2 over theta 1. So for this one, it's really just an algebra problem from here on. So N1 is the glass, so it's going to be 1 over N is going to be equal to theta 2, which is 4.64 times 10 to the -7 over 6.5 times 10 to the -7. The -7s are going to cancel. Notice here that it's 1 over N2, so we can take the reciprocal. So N2 over 1 is going to be 6.5 divided by 4.64. And we grab our calculator and work it out. 6.5 divided by 4.64 is 1.4008. So they give it to you here in 2 decimal places, so we're going to take 2 decimal places. So 1.40. So N2 is 1.40, and now we can use, before we do that, of course, we have to check our calculator, make sure that it's in degree mode. It's in radian mode, so let's change that and get out. Okay. N1 is 1, so don't worry about it. So sine of 30 degrees is equal to 1.4 times sine theta 2. We want to solve for theta 2. So sine of 30, I'm pretty sure that's going to be a really nice number. Sine of 30 is half. So 0.5 is going to be equal to 1.4 times sine of theta. So let's divide both sides by 1.4. Let's move it up here. So sine theta is 0.5 divided by 1.4. So theta 2 is going to be equal to sine inverse 0.5 over 4. It's going to give us that. Sine inverse of 0.5 divided by 1.4 is 20.92 degrees. That's our answer. So now we're told that Matthew notices that if it keeps increasing the angle, the ray of light bounces off the inner surface of the glass as shown in the diagram below, and none enters the air. Name the phenomenon which is appearing. So it's total internal reflection, refraction, reflection, because now this boundary acts as a mirror. Right, now we're told to describe the conditions needed for this phenomenon to occur. So there are really 3 phenomena. N1 must be greater than N2. So the refractive index of where it's coming from, this grey bit, must be denser than the refractive index of the air or anything really. So that's one thing. The next thing is that the angle of incidence, so that's theta 1, must be greater than the critical angle. And they say don't work it out. So just trying to dumb the question down, I suspect. I'm going to do that in this case. The third one is there has to be a clear boundary. It has to be a clear boundary. So you can't sort of have the surface as being kind of like that, because it's not going to work. There has to be a clear boundary. It can't be a gradiated boundary, and it has to be a uniform substance to uniform substance, mostly. All right, let's work out this critical angle. It's not asked for, but I'm just going to. So here's the boundary, and this is N1, and this is N2. So I'm going to say that this is glass, and I'm going to give it a critical angle, refractive index of 1.5. And it says yes, I'm going to say the N is 1.0. So here is our normal. This is theta 1. Now, at the critical angle, this angle here is going to be 90 degrees. So it's going to hit it and it's going to skim across the surface. Anything this way from here, it's going to bounce back in as shown. So theta 2 is going to be 90 degrees. And it's going to make our life a lot easier, because I connect to Snell's law, N1 sine theta 1 equals N2 sine of theta 2. Sine of 90 degrees is 1. So this just goes to 1. And N1 is going to be 1.5, so it works. So theta 1 here is going to be our critical angle. So N1 is 1.5 sine of theta, and I'm going to set theta 1 under theta critical equals N2, and N2 is 1 in this case. So I'm going to divide both sides by 1.5. So sine of the critical angle is going to be 1 over 1.5. So the critical angle is going to be sine inverse over 1.5. So sine inverse 1 divided by 1.5, 41.8 degrees. So anything greater than that, it's going to totally internal thing. So this is a really, really useful property for things like fiber optics and just general optics. It's really, really useful for them. On to question 3. Wireless internet connections, Wi-Fi, work by sending information as electromagnetic waves through the air. What type of wave is an electromagnetic wave? With the propagation of electromagnetic radiation, I think what they're looking for here, they want you to say that it's a transverse wave. It's actually a really, really interesting one. It's kind of a double wave. You have the electro wave moving perpendicular to wave which is moving the magnetic bend. In fact, I'll show a little thing for you here. Again, I'll show you. I'll leave the link in the description. So here we have a plane, and this is the magnetic field. Yeah, that's the magnetic field, and this is the magnetic field. So they kind of work like that. There are sort of two waves. So that's the electric, that's the magnetic. And they work perpendicular with each other, but they are transverse waves at the end of the day. Wi-Fi interference can be an issue in a populated school environment. This occurs when two or more Wi-Fi access points are using the same channel frequency, causing interference and reduced reliability of the Wi-Fi. Explain how having two Wi-Fi access points in waves at the same frequency can cause both spots of strong Wi-Fi signal and spots of weak. Well, there's going to be constructive and destructive interference. So you would need to say that somewhere. In fact, I'll do another little sim so you can see what this looks like. So imagine these 2 points are Wi-Fi transmitters. If we have one going, it's going, here's the peak in node, and it's moving out at the speed of light. That's fantastic. So they're moving out like that, easy to pick up. If we have another one which is set to go the same frequency, we're going to get this pattern. So after a while, a pattern will emerge. So we have really, really strong, weak, strong, weak, strong, weak, strong. And here we have this node here where there's nothing. They permanently delete each other. And then if we move slightly, it's going to be really strong, really weak, strong, weak, strong, weak, strong, weak, strong. They interfere with each other. It's a really, really bad situation if your computer is trying to do things, because it downloads things as packages. So if it gets a bit of one package missing, the whole thing is dead. It's a real pain in the neck, and there's a real art and science to set up a Wi-Fi network when you have more than one transmitter. All right, question C. Internet satellites orbit the Earth at a height of 550 kilometers. The wavelength of the radio wave is 0.025 meters. So we've got here lambda is 0.025 meters, and it's in meters. How many radio waves reach the Earth in 2 hours? And here there's a picture of satellites. Satellite looks like it's here looks more like a TIE fighter than a satellite, but you get the picture. How many radio waves reach the Earth in 2 hours? The velocity is the frequency times wavelength. That's given in the formula. Do we know the velocity? Yes, we actually do. All the waves, the vacuum at the speed of light, which is 3.0 times 10 to the 8 meters per second. It's in meters, so it's complex. So now we need to work out frequency. And it's pretty much just algebra. So 3.00 times 10 to the 8 is equal to the frequency times 0.025. And this 550 kilometers, but I think it's a red herring. So the frequency, that is how many pulses in hertz, that is going to be 3.0 times 10 to the 8 divided by 0.025. So it's going to be an enormous frequency in hertz. But let's do our calculation. It's from the last one. So 3.0 times 10 to the power of 8 divided by 0.025. And it's going to be a huge number, 1.2 times 10 to the power of 10. If you're interested in the unit, it's going to be hertz. It's going to be waves per second. How many seconds are there in 2 hours? Well, 2 hours. 2 hours times 60 minutes times 60 seconds. 2 times 60 times 60, 7,200 seconds. So this every second for 7,200 seconds, 1.2 times 10 to the power of 10 times 7,200 it's going to be an enormous 1.2 times 10 to the power of 10 times 7,200, and it's going to be 8.64 times 10 to the power of 13, which is a huge number. So it's going to be what? 864, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13. A staggering huge number. But that's how many wavelengths it to hit the Earth. Last question. When a Wi-Fi signal passes through walls, they slow down. The boundary between wall and air can be modeled by ropes of different densities joined together. The diagram below models two pulses in two Wi-Fi points traveling towards each other. The speed in the air is 2 squares per second. The speed in the wall is 1 square per second. Describe how the frequency of the Wi-Fi signal changes as it moves from the air to the wall. And this is, of course, a trick question. It doesn't change. Velocity changes, wavelength changes, but the frequency doesn't change. So assuming that any pulse is half the height of the original after it transmits and reflects with the boundary, draw the result of the two pulses interaction after 3 seconds. Right. So we've seen what that means. So the interaction after 3 seconds. So the pulse is going to half as it passes over the boundary and reflects. And remember, when it goes from light to heavy, it's going to invert. And when it goes from heavy to light, it's going to stay. Now, we're told that the air in the light rope velocity is 2 squares per second, and velocity in the heavy rope is 1 square per second. After it hits there, after this wave hits, it's going to halve in size, but it's going to increase in its velocity. And if this one hits, it's going to halve in velocity, and it's going to invert half its size. But let's kind of look at it. This wavefront here is going to be moving at 2 squares per second, and it's for 3 seconds. So this wave right here is going to move 1 second, 2 seconds, 3 seconds. So it's never actually going to hit boundary in that 3 seconds. It's moving too slowly. So in our little model here, it's 3 up, 3 across. So in our little model here, it's kind of used this now working down here. And this is going to be, so here, this is going to be 4. So it's going to be 3 up, 3 across, 3 down. It doesn't move forward. Right. Now let's have a look at the second one. This is where it gets interesting. It is going to hit this boundary, and it's going to do 2 things. It's going to slow down, lose magnitude, and it's going to reflect. And it's going to reflect losing 1 square, but it's going to stay inverted. So let's do this one in red. So this one is going to move ahead 1 square here for the first second, and then 2 seconds, and then 3 seconds. So the wave front is going to be there, but it's also going to be moving twice as fast. So it's going to go like that. Now, when it hits this square here, this wavefront here, it's going to reflect, and it's going to go down 1. So after 1 second, 2 seconds, 3 seconds. So it's going, the reflection is going to be like that. So we have like this square here of magnitude 1, which is 1, 2, 3, 4 in the white, the light coloured section, and 2. So 6 across, 4 and the white and the clear one. So 1, 2, 3, 4. So that's where this wave is going to be after 3 seconds. And now we have the aggregate. We have to aggregate this. So let's do that one in black. So this is 1, 1, 2, 3, 4. So it's going to be the, and then it's going to be 4, 4, 4, 4, 4. And then it's going to go to, oops, there. Then it's going to go down, and then it's going to look. So our square is going to here. It's going to come up 4, across 3, down to down, and across 3. So that's what it's going to look like after 3 seconds. So I'm going to say, well, this is our working, and this is our actual answer that we want. And that's the end of the exam. My thoughts on this exam, a little bit disappointed. I thought it was good on the easy side. Tell me what you think, and I will leave the links to the simulations that I used.